Hello, everyone, and welcome to today's webinar. We're about to get started. Just to kick things off, a couple introductions. My name's Lyle Mraz. I am the president here at Xiris Automation, and I'll be acting as your moderator today. I'm also pleased to introduce Cornelius Sawatsky. Cornelius is a sales manager here at Xiris for our Weld inspection systems, our WI systems. He's been with us for over 20 years in various capacities, including engineering and field support, and for the last 15 years been specialized in helping tube and pipe producers like yourselves to implement our WI system, help improve your welding process. So we're really lucky to have Cornelius as our presenter today and for him to share his wealth of experience with us. So today's topic is the Xiris Weld Inspection System, and specifically designed for helping tube and pipe producers to improve their weld quality. We're going to learn about many of the benefits, and we're going to learn a little bit about how to install these systems and some of the logistics around that. So if you're a quality manager, a production manager, plant manager, this webinar should be of real high interest to you. So excited to get started. Couple housekeeping items. Number one, we do have everybody's microphones on mute just to keep down the background noise, but we do want your questions. If you look at the top of your screen, you'll see a Q&A button. Click that. Type out your question, and we'll set aside some time at the end of the presentation to address those questions. And please do stick around for the questions at the end of the webinar. They can be very informative. The webinar today is going to be about 30 minutes, 20 to 30 minutes, and then we'll have 10 or 15 minutes available for questions. The webinar is being recorded, and we'll send you a link to that recording by email. As part of that email, we'll also send you a WI white paper that will be of an interesting read for you after the webinar as well. So that's it for the housekeeping. Happy to hand things over now to Cornelius. Take it away, Cornelius.
Lyle, thank you very much for the introduction. I appreciate that. Certainly, we often have conversations with our customers around their production and keeping the mill up and running. Some of these words are very common words that might be familiar to many of you, and they might be part of your Monday mornings or your weekly production and meetings. Certainly, these are words that we often hear about trying to keep the production running through the mill continuously. Certainly with many people, for example, particularly picking on those making automotive tubular products, you have such a high changeover rates, the frequency of your changeovers, and that really does impede your production capabilities. And so in order to try to work on some of these topics, one of the things is to look at, how is the welding process made? And what's the stability around it? Now, you will, of course, be familiar with traditional NDT systems. Think about flux leakage, ultrasonic, eddy current. These are your final inspection solutions that you use at the end of the mill to make sure that you don't have non-conforming product coming off the mill. Just very briefly, and I'm sure you're all very familiar, eddy current and ultrasonics, the likes, you're inducing an energy into the tube or pipe. Think about eddy current. You're putting in a magnetic field, and then you're reading back that magnetic field, and you're looking for sudden changes. In the case of when we want to go further upstream and look at the welding process, then now we need to look at a geometrical type process where we project a laser line across the weld zone, look at that through a laser line through some filters onto a sensor so that we can start making measurements. So when you think about your eddy current and ultrasonic as your final inspection at the end of the mill, what if you could see a change on your mill as it happens and respond to that? And so that's kind of what we're talking about here. So when you've got that laser line projected onto the surface, this is a representation of what the operator would see. So very briefly, this white line that we see on this image here, that is the OD surface profile of the pipe itself. So think about it when you're taking a section of pipe and you're holding it and kind of looking down, right? You're looking at that OD surface, and that's basically what this representation is. We can then have the software do a circle or an arc fit to that profile and start making measurements. As a quick little example, in this case here, this red line here representing a perfect round circle. On the left side here, it's fitting up very well. And on the right side here, it's a little bit higher. So left minus right, we have a difference between the two of just over 1/1000th of an inch. Very minuscule in this particular case, and that's great. But that's a very high resolution view of it. There are, of course, challenges when you're right at the back end of the well box. Steam and the amount of particulate in the air is for sure an issue. And so the question comes, well, how do you manage it? And so what we've done here, so if you look at this being the sensor head that is at the back end of the well box being just to the right here, and you can see the glowing bead. As I play this video, you will see that there is a lot of steam. And so the way that we mitigate that is we've got a block on the bottom of the sensor head here that's held in just by a simple pin. And that block looks like this. It holds a cover window. And so that is so that it can be readily removed and swapped out with a clean one to continue production. So the process usually is only about 30 seconds to do that swap out. Additionally, there is an air hose connected to the top that's taking a little bit of shop air and pushing it down into that little cavity there, which keeps some positive airflow underneath these windows to keep that steam from actually coming up. And so as a result, we're able to keep these windows quite clean. Depending on if you've got projectile of water splashing, that is a little bit different, but typically you might do a swap out or a clean on a once or a shift, maybe once a day. We have customers who do it once every couple of weeks. Kind of depends on just what the environment is, but that's roughly what the setup is. And so when you think about that steam, by the time we've dealt with it, that's the clarity of the picture that the operator will see. So this is a recording of that same system from the operator's perspective. You see that that is quite clean. And just very briefly, when you look at it, the other thing that you have as an instantaneous feedback, for example, the width of the weld bead, it had a slow creep up. Something was adjusted on the mill and it came back closer to nominal. And so you can see instantaneous feedbacks on the mill that way as well, right? So each of these measurements, you can set your working process parameters. There are multiple configurable measurements available, and then each has their what we call the green, yellow, and red, or good, warning, and fail limits. And they're represented on this bar graph. So this faint gray line is your warning line. So if your process starts to approach that, then the number would start to go yellow, and it would be indicated on the light tower as well that it would start to turn yellow, saying, hey, start paying attention to me. When it goes right to the edge of the window, that's when we tag it with a red mark. The number would have been colored red. the light tower would be red, and the buzzer would go off, say, hey, get over here, I need some help. And so operators are able to use that as a real-time, quick response to any process variances. Furthermore, if you have an alarm situation, that can also be outputted through a digital I/O block. So if you wanted to tie it into your existing PLC for any functions there, or this can be tied to a paint marking system. Sometimes customers will even utilize the existing paint marking system from their eddy current system. Just tie this one in as well, and that certainly can be done. Some customers get a little bit fancier and they use a different color paint for this system versus the NDT system. And so just to be able to differentiate what had caused this tube to be rejected. Some of the most popular measurements that people like to look at, and I'm going to focus on the high frequency welded side of it. So mismatch is a big one. Eddy currents and ultrasonics, when you're dealing with a heavier wall pipe and you've got an oscillating ultrasonic head, for example, you can pick up mismatch. But when you're dealing with the light weld tubular components, particularly, again, think about automotive or even many of the structural, you're dealing with a much thinner wall, and then the ultrasonics don't work as well for finding mismatch. And so that's where this one is very popular. Depending on the type of product, so when you think about some basic structural, 10% of wall thickness is a very common number to use for your maximum mismatch allowance. Then you've got a scarfing tool that cuts that bead off at the top quite nicely and makes it look nice and round and uniform. And what you've just done is created a thin section on your material, right? Or if you're not cutting quite enough, you leave a little step. Most commonly, people will use their thumb to scratch across that weld zone to see if they can feel a mismatch. And we've demonstrated to customers that the thumb is calibrated to about 4/1000 of an inch. And much less than that, it becomes more unreliable, right? Now, if you go into the automotive secular tubes, mismatch is a much tighter tolerance, and many automotive components will specify a maximum of 5%. So if you have a tube that you're running with less than 1 millimeter, think about a 0.8 millimeter wall thickness, not uncommon in the automotive industry. 5% is a very tiny number. And it's not something you're going to feel with your thumb. And so that's where this becomes quite important. So we worked with one customer a while ago. It's been a few years ago now. They had a substantial set of weld failures post-process. So in line, they had ultrasonic, they had eddy current, and they had flux leakage. And their audit destructive test periodically was acceptable. But what they were finding is when that tube was then being used further downstream in another operation, things like hydroforming, bending, those processes, then they also induce a lot of stress. And now all of a sudden it's the entire tube that needs to be with a strong weld, not just that one sample where you might have done a random audit test. This particular customer was running a dual phase material. And so it's, for those of you that deal with dual or multi-phase material, you will know how challenging it can be to run on the mill. And so mismatch becomes a big factor. What this customer discovered is that if they set their maximum mismatch limit to 3% of wall thickness, they were able to eliminate 90% of those weld splits. So that was a very fascinating experience for them. Another metric that people do like to pay attention to is the amount of squeeze out. And so again, depending on the type of product, depends on how high that bead will be, but generally speaking, any of the surface material you'll want to squeeze out so that you don't have any impurities or entrapments within the weld bead itself. And so by monitoring the height of the bead, you're able to determine how much you are squeezing out. That metric can be expressed in either just as a height or as a volume-based calculation, so bead width and height components as an area calculation. So there's different ways of expressing that. So we have customers that monitor that as well. Another favorite is what we call freeze line. And you will often see, if you observe an operator on the mill, they'll take their pliers, hold a piece of scarf material, and they'll look at it and twist it. What are they looking for? There's a couple of components. One of them, of course, is how uniform is their scarfing, cutting on either side of the bead. But the other one they do look for is whether or not they've got a groove at the top of the bead. If you have a groove at the top of the bead, that first of all, we know that we didn't squeeze out all of the surface materials, right? So we are at risk of entrapments. Furthermore, it's a great indicator that you might actually not have had enough heat for it to properly blend together. And so it kind of stayed a little bit placid and just kind of force itself out a little bit, and you get those knuckles pointing up, right? Some people will even imply that that is an indicator of a cold weld. Because we're not actually measuring temperatures here, we're not going to claim that it is a cold weld, but it is an indicator that it could be. So those are the three most popular measurements that people on the HF welded side like to look at. Where on the mill do you get the most benefit out of it? After welding, before scarfing. That is where you have all the as welded information, right? And then we do also have people, for example, in the fuel tubing industry, hydraulic tubing. So places where you have requirements for very uniform surface conditions. On a hydraulic pipe, it's high pressure, so you need a strong weld. Often you're using a compression fitting, and so you need that very precise uniform surface condition. And so if you monitor how the bead was scarfed off to see if you've left a little step, may be the cause of mismatch, or usually the cause of mismatch, or if you've been cutting too deep. So we have customers that will actually run double sensors on those types of applications. 70% of the value is before scarfing, and then we've got a small segment of it after scarfing as well. So when we kind of wrap all of it together, this was a video recorded during a demonstration on a tube. It was a 76 millimeter diameter tube, and it had a 1.9, I forget the exact number, around 1.9 millimeter wall thickness. So think about an 0.75 wall around there. A few things to think about on this before I play the video. If you take the letter HF up here just as your reference point, that bead is well aligned here. So one of the struggles, so first of all, I guess, if you were to look at this screen, instantaneously, you will see that there's a lot of instability on that mill without even looking at any details, right? So let's start getting into those details. What's going on? We've got a very high frequency. Well, first, we've got this slow snake here. Let's call that the low frequency oscillation. Then we have another one that is a very high frequency oscillation within it. There were two symptoms in this particular case. Number one is they had what we call strip buckle, where one side of the strip was waving. And that generated this high frequency mismatch. Then additionally, they actually had the tube rolling back and forth slowly. And that's actually represented down here by the bead position. coming in and out. And you will see that when you take that HF reference point, that bead will move over. So as I play that video, and I'm going to momentarily pause it, if I can. So we momentarily pause it. We just happen to be a little bit on the higher side, but it's well rolled over, right? If we, again, play it just a short second, now all of a sudden you see you've got a much bigger mismatch. And now it's gone the opposite direction on the mismatch, right? So one side was a strip buckle, but then as it rolled over, it polarized which way the mismatch went. So for perspective, the limits on this particular case were set to 20% of wall thickness. The fun fact here was, and I personally did this demo, I took a 1 meter section of tube and I asked 3 different people to go and measure for mismatch. They all came back with different answers, and they didn't necessarily pay attention to where the other person had made the measurement. And so that was just an indicator. So when you just visually look at it, you don't see that instability. That looks good. So your thumbnail scratch once every 10 minutes, it's fine, right? But when we look at that high magnified view, we all of a sudden get a lot of detail on the instability of that mill. And so actually now in the video, I can see it nice and clear. It was a 1.9 millimeter wall thickness. So overall, when you combine that, and you've got that instantaneous feedback, all of a sudden you start to impact what we started to discuss with in the beginning. You know, we're identifying variabilities within the mill much quicker, as well as having that visual representation and able to take corrective actions. One of my favorite things was at a customer where 3-shift operation. We all know each operator has their own finesse as to how the mill should be running. And inevitably, we're familiar with the scenarios where A shift operator has been running production great all day, B shift comes in, something is wrong on the mill and we need to change it. So here we have a tool that is a common communication tool between the two and keep that mill running stable. The other thing, what happened at this particular customer was it became a competition. Well, how close to zero can we keep some of these parameters, and how minimal can we keep the variations? So as the heads and tails of a coil come through, inevitably some things change a little bit. So they can just very quickly nudge the weld box a little bit and use their magic art. I do call these welders artists with a hammer, and able to get a more good product off of that strip coil instead of throwing away the last 20 feet and the first 30 feet of a coil. So that is a bit of the conclusion of the presentation. I do hope that you found it helpful, and I'm wondering if we do have any questions in our Q&A at this time.
Hey, Cornelius. Yeah, we got a few questions here, and encourage everybody to stick around for the Q&A. And also, if you do have some questions, go ahead and pop those in, and I'll keep an eye out for them. First question, what's the minimum and maximum diameter the WI system can handle?
Fantastic question, Lyle. Thank you. We have a number of sensor heads, depending on the application. Similar to a eddy current system where you've got different types of coils for different diameters. We don't have to be that precise. We've got a handful of units where we've run tubes from as small as a 1/4 inch diameter. Think about refrigeration tubing. As well as we've gone all the way up to a 32-inch pipe. So think about an API series pipe. So you're running from around 3-inch to 9-inch diameter. You can pretty well cover that with one single sensor head. So there's a fair amount of overlap as to which sensor head can run what diameters, but that's kind of selectable there.
Okay, perfect. Thank you. Next question. Do you have anything measuring the temperature of the weld? This will help better understand what's going on with the welder.
So again, great question. On this unit itself, it does not measure temperatures. That's where I made that reference earlier on the freeze line. We call it freeze line because it could be temperature related, and that's just a common term being used. But this particular unit does not measure temperature. We do separately have another unit called the HF pre-weld. There's a thermal camera-based system looking directly at the V. Many of our people in our audience would be familiar with pyrometers. Often people will have a pyrometer right after the weld to check the weld temperature. That's a single spot measurement on the bead. Our thermal camera actually looks at the V going right into it.
Okay, perfect. Thank you. How do you set the system up with two cameras, one before and one after the OD scarfing?
So quite straightforward. The HMI controller, which you saw in one of the video slides, it actually has the capabilities to run two sensors at the same time. And either you toggle between which sensor you have displayed, or sometimes people will put on a secondary display monitor so that they have one sensor displayed on each screen.
Okay, perfect. Next question. Will this system be able to replace a traditional NDT system?
Unfortunately not. I wish it could. There is no one technology that I'm familiar with that would serve as the complete end-all be-all inspection systems. You'll have products that have specifications that call for a ultrasonic type inspection or an eddy current with a hole drill size of a specific parameter that has to be detected. This, unfortunately, is not a replacement for those types of specifications. This is in addition to additional tools where this is more of a process feedback as opposed to fail or go, no-go situations.
Okay, perfect. Next question. What's the min and max distance from the tube surface to the sensor?
There really are only two, depending on the series of sensor we're using. The 3000, which is what is most popular for the HF welded segments, the sensor is about 75 millimeters or 3 inches above the surface of the tube. The 2200 series, which is more used in some of the TIG welded and laser welded applications, or the really small diameter HF welded, that sensor is only about a 1/2 inch above the tube. And most tube melts are bottom based, so if you're changing diameters, then the height of the sensor has to be adjusted accordingly. And that's typically done just on a screw dial adjustment slide.
Okay, perfect. Next question. Do you have an example of laser welding?
I don't have an example of a laser weld on this slide deck, but we certainly have many of them. So I would encourage reach out. I'm happy to share an example of that. I just don't have it in this slide deck, but we've done many laser weld applications.
Okay,
and that's
perfect.
actually what I can go back and actually point out. One of them, I do have one indicator here. So on this particular slide, there's this measurement undercut. That's actually a very popular measurement for laser welded applications because of how small that laser spot is. It's very easy to be a little bit off that seam, and then we end up with just a tiny little groove on the side of the bead, and we call that undercut. So that's definitely the closest example I have in this slide set.
Okay, perfect. Next question. Can you or how would you identify small holes and weld split?
So small holes are very difficult to detect. If you have an actual hole, that's what the eddy current is designed to detect, right? We're again looking more at the process stability and variations. And so think about if we did have a freeze line, right? That's a process related. If you just had a momentary hole that you drilled into the pipe and ran that through, chances are that that's not what we would pick up. Because we are so far upstream in the process, we are susceptible to that steam and potentially water particulate on the tube surface. So we have to do a little bit of momentary filtering. We're making 100 measurements per second. But if you're running at 300 feet a minute, you can imagine that, we've got 1/4 inch gaps between measurements. So a small hole we wouldn't pick up during that time.
Okay, thank you. And someone's just got a comment. Maybe you can elaborate on this, Cornelius. But what they said is one of our customers told us when the outer weld bead shows large, it usually means that the inner bead is large too. This can be resolved with mechanical adjustments on the line.
For sure, there are variations and implications on it. So if you're dealing with really light wall material, again, automotive tubular category, that statement is perhaps reasonably accurate, that there's a fairly good correlation between the ID bead and OD bead. May not be the exact same size, but a decent percentage of it. When you get to thicker wall material, it really does depend on the presentation coming together. So if your fin passes are properly preparing your edges and you bring them together pretty well parallel, then yes, you could make that assumption. But if you are presenting them where your ID makes contact first and then squeeze more of it out, you'll end up having more flow lines coming up, and therefore that ratio may change. Unfortunately, and by the time we put enough laser energy in to see the ID bead, we've melted the entire material. So it's not something we can do, but some assumptions can be made.
Okay, thank you.
But there's many disclaimers for that one.
Right, okay. Another question, when there's an absence of a freeze line, is that indicative of not enough heat?
It's more the opposite. If you have a freeze line, is the indicative that you probably don't have enough heat. It's when you have no freeze line, then that's just a nice uniform bead, like what you see at the top here. So in this particular example, actually, you see that you've got a 1/1000th of an inch freeze line on a 188 wall material. This is a 4.3 inch pipe. That's just because we've got a little bit of a concavity at the top. This is not a concern whatsoever, right? So in this case here, this is carbon steel that's been well squeezed together and well heated.
Now we've talked, the presentation kind of covers round pipes and tubes. Can this work with rectangular tubes?
Yep, certainly we've got profiles in there for various types of profiles. So we've worked on where the weld is presented on a flat. So think about square or rectangular tubes. Very often it's slightly welded on a peak. And so we would still be able to monitor that deflection and how much of a peak that is being presented at. We've also done applications where the weld was near a corner, and so it really presented on the screen as what we call a dual radius. One of the sides was a relatively large radius, and then the other side was quite small, representing that corner. So that can be done as well.
Okay. And looks like possibly our last question here, but does the system require initial calibration and recalibration?
Great question. So, of course, when the equipment is shipped out, that is calibrated. The sensor heads are sealed up. And so there's no internal moving parts. So that part is quite well. Some of our customers, what they'll do is they'll maintain a known reference sample that they'll sometimes put underneath there just as an audit. Are we still getting a similar reading that we anticipate? We do encourage customers to do an annual calibration check. We call it a recertification, where we can have a service tech come on site with a calibration set where they put the sensor head into and check it. And sometimes, maybe they do need to make a bit of a software adjustment for that calibration, and that's fine. They can do that, then issue a new certificate for it as well. So that's an annualized option. If it needed physical changes internally, the sensor would have to come back to the factory. That's not a very common occurrence, but it can happen.
Okay, very good. I think that brings us to the end of the webinar, and that's the end of the questions. So first of all, thank you to everyone that attended today. Appreciate your interest. You'll get an email from us with a link to the recording of the webinar for future reference. And we'll also send you that white paper that I mentioned earlier. And a special thank you to you, Cornelius, for sharing your experience with us and telling us more about the WI system. Certainly, if you have more questions, once you get our email, that'll have our contact info. So please reach out if you want to schedule a demonstration, if you'd like some pricing information, and so on. Don't hesitate to reply to that email once you receive it. That's it, everybody. So have a great rest of your day, and we'll see you at the next webinar. Take care. Bye for now.
Thank you, Lyle, and thank you to everyone in the audience for participating. We appreciate it. Have a great day.